Assalamu alaikum wa rahmatullahi wa barakatuh. Yeah, once again, welcome to physics class. Today, we continue from where we stopped the last class we had. So, today we are moving to current electricity. And in current electricity, what we shall be taking note of under this are current. What do we mean by current? Potential difference, resistance, factor affecting electrical resistance in cell, circuits, and the likes. Now, when we do talk of a current, we define current as a quantity of charge flowing in a circuit per unit time. That is the quantity of charge before we can say a current has flown, there must be a charges. So charges now, which is we have quantities of charges flowing, quantity divided by the time taken for the charge to flow is denoted as current. So we can define current as the quantity of charges flowing per unit time. So we have that the unit of quantity of charge is denoted as coulombs. Q, we denote coulomb as Q, and time is T. So that means that we say that current R equals to Q over T. Take note, current can be estimated by using the charges flowing divided by the time elapsed. So that is for the current. Likewise, potential difference and current can be measured by many devices. As I have with me here, this is what we call ammeter. You can see that here A is written on it. So what this does is that it quantifies the current flowing through this ammeter. Okay, so this quantify a current, and likewise we have other devices that measures current. This is also known as a galvanometer. You can see G is written on it. You can also see it. So this also measures the amount of current that has flown. And likewise, we have many other devices like micrometer and the like. So when we talk of potential difference means that the difference in volts between the two terminal. We have electric cell. The difference in volt between one terminal and the other one is defined as the potential difference. And potential difference, which is denoted as V, it is measured in volts. It is measured in volt. That means that the unit of potential difference is a volt. It can also be written as small letter V. Take note. And that one can also be measured by using voltmeter. Wherever you have a device in which that V is written on this, as you have it like this, so this is known as a voltmeter. So it is used for measuring potential difference. And likewise, resistance. Resistance means that the opposition of charges. As you have a conductor, if there is no how the efficiency of the conductor is we will have some little resistances. So the opposition of the material to the flow of electric current, that is not wanting much of current to flow, is known as resistance. So resistance, it is denoted as a R. So we have capital letter R and we have small letter r. This capital letter R, all R stand for resistance, right? But capital letter R, this big R, it stands for external resistance. External resistance. External resistance. While small letter r stand for internal resistance. Internal resistance. And where do we have external resistance and where do we have internal resistance? External resistance is the resistance flowing in the circuit. This resistance flowing in the circuit is denoted as a external resistance, while the resistance of the cell you are using is known as the internal resistance. So all these ones are among the terms we use in current electricity. Now, before we start the factor affecting electrical resistance, let's talk about an electric cell. Electric cell. Now, we define a cell as the smallest unit of life in your biology, right? Likewise in physics, electric cell can be defined as something that which it produces the electrical force in driving charges from one point to another. If you want to move a quantity of charge from one point to another, that means that it requires a force, and that force can be supplied by what we call electrical cell. Now basically we have two types of cell. We have what we call primary cell, and likewise we have secondary cell. Now what do we call a primary cell and the secondary is that we have some cells that after you have used up the energy composed in them, they cannot be replaced after use. So what you do is that you try to let the thing, you dispose the cell after it has been used up. So once there are some after it has been used up, you can still refill it again by recharging again. So this is what we call a secondary cell. So a cell that cannot be refilled after it has been used is called a primary cell. And we have example of such. We have Daniel cell, right? We have Daniel cell, we have Leclanché cell. So all this come from name of someone, Daniel. So Daniel was the one that invented Daniel cell, and likewise Leclanché. So all these examples of cell are under primary cell, and their aim is that after it has been used up, they cannot be replaced. So you dispose the cell. So the one that can be refilled after it has been used is called a secondary cell. So it is called a secondary cell. Now, if you have two or more cells, it is called a battery. So that means that if you have two or more cells, definitely there must be a way in which that they are being arranged. That means that it is either they are arranged in parallel or they are arranged in series. Let's look into this connection now. Let's say that a cell is being denoted as a two unequal perpendicular line like this. You can see two unequal perpendicular line. So this one now, it stands for cell. Let's assume that we have another cell again. This is another cell now. So we now call this, okay, we have two cells, more than that. If case arises, so this is called a battery. Now, so we now determine how does current get into each of the cells you are having. Now, if the same current flows through each of the cells as you have here, let's assume that a current is flowing here. You will see that once the current enters, it's the same current that will move to the next one. That means that whatever current you are having here is the current you have for this one as well. So let's call this one A, cell A, and this is cell B. That means that whenever the current of cell A is the same thing as current of cell B, we now call that kind of arrangement as a series arrangement. Unlike when you have cell, let's say that this is cell A now, this is another cell B. Now, so this is the current. Okay, let's assume that we have another cell making it 3 cells. So now let's assume that the current flow is entering the cell like this. Now you will see that from this diagram that the current that enters here, cell A, will be different from the current that is entering cell B, and likewise that of cell C, in such a way that not equal current flow in each of the cells. That kind of arrangement of cells is called parallel arrangement. Now, how do we now calculate the equivalent amount of EMF in cell when they are in series? So from the series connection now, we now say that the summation of the EMF in this cell now, which is the E total equals to E1 plus E2. Just add the all the cells you are having, the EMF of the cell you are having, add everything together to give us the equivalent of the total EMF. Now, but if you have cells arranged in parallel, many cells that are arranged in parallel, one thing about parallel arrangement is that they will have the same EMF. For example, let's say that cell A now is 1.5 volts, cell B is equals to 1.5 volt as well, while cell C 1.5 volt. So all these one are 1.5, they are arranged in parallel. So the total EMF here is that you pick one EMF out of the entire EMFs you have. So if you have more than 3 as you have written here, so definitely it is the EMF of one out of the entire EMFs, entire cells you have. So that means that from this parallel connection, I will now say that our E total here equals to the EMF of any one of you. We will say that 1.5 volts. I hope that is clear. So unlike when we have series, you add everything together to give us the total EMF for that series arrangement. But if it is in parallel, you choose the EMF of one out of the entire EMF. And mind you, they will all have the same EMF. Now, this is about cells and the likes, arrangements which is a parallel or series. And now, as you have said here, the small letter you have underneath is called the internal resistance of the cell A. If you have another one here, tele now is the internal resistance of cell B. So as you have 1.5A, there are some diagrams you will be seeing that beneath the perpendicular line, you will just say, let's say 1 ohms. So this 1 ohm stands for the internal resistance of the cell, one of this cell. I hope you got that. So you have for this, it might be the same, and likewise it might not be the same. So you also look for the series parallel arrangement of resistance, internal resistance for that one, to calculate your total resistance for that one. Now, so this is how to get the total EMF in series or parallel. Now, so as you have this shape, cell, current, and any other thing like this. So this is the background, this is our battery again. So let's say that this is your ammeter now. This is where you are getting the value of current now. So this diagram, that is a part that have been created for the flowing of electric currents, is called an electric circuit. I hope you got that. The part for the flowing of electric current is called electric circuit. So after this one, we will verify some circuit and see how we can calculate current, resistance, or potential difference. So this is one of the arrangement of series or parallel. So one of this, as I have with me here, this is one of the examples of a primary cell. You can see in primary cell, basically is that you have a composition of chemical energy inside of it, right? So that blacking something, it is either a solution of dilute H2SO4, dilute tetraoxosulfate 6 acid. Now this tetraoxosulfate 6 acid now serve as the electrolyte. It serve as the electrolyte. We define electrolyte as a compound in solution, so that creates the electrical energy used for the transfer of charges in an electric cycle. So an electrolyte can also be a solution of ammonium chloride, NH4, ammonium chloride. So as I have with me now, example of this is a typical Leclanché cell. Leclanché cell has two types as well. We have the dry type and the wet type. As I am holding now, this is a form of a dry type. So you have one edge at the top like this. So this is called the anode, which is also known as the positive terminal, and we also have the cathode, which is the negative terminal. So this is a typical example of a dry Leclanché cell. And one of we have some disadvantages of primary cell or defect of a primary cell. The two defects of a primary cell. Defects of primary cell. Primary cell. The two defects of primary cell are, we have what we call polarization. Polarization. And we also have local action. Local action. Now, when we have a cell in which that there is a formation of hydrogen bubbles, let something like a tutu coming out of this positive terminal in such a thing, that is called polarization, and it is one of the defects of this kind of a cell. I think you are following. So that process is called polarization, and how to correct that polarization is by using a depolarizer. A depolarizer. An example of a depolarizer is what? Magnesium magnesium 4 oxide, MnO2. Okay, so this is what we call a depolarizer. We use it to correct the processes of polarization. And then the other defect of the primary cell is the local action. Now, when the negative terminal of a primary cell, when we have something that reduces the contact of the primary cells at the cathode as I am holding now, so that action is called a local action. And how do we correct that is the processes of amalgamation. So what you do is that you get a mercury, you will be continuous rubbing it, because it is because local action is it causes an effect to the zinc electrode, which is the negative terminal. So if you now have a mercury, by rubbing it along this plate, along this zinc plate, so it will correct that action, which is, and that thing you are doing now, rubbing this zinc plate with mercury is called amalgamation. So we use amalgamation to correct local action. So all these are defects of the primary cell. So primary cell, polarization, and then local action. And take note of how to correct those defects. And then the electrolyte we have in a primary cell, which can be dilute tetraoxosulfate, cis acid, or ammonia chloride. So this is under cells now. So as you have electric cell, let's try to draw the shape of one electrical cell. So as you have a cell, for example, you have a diagram like this. This is one cell. This is another cell. So you have a current. Okay, you have resistance now. So we have a resistance, and we also have an amplifier here. So as you have an electrical circuit now, so this symbol you are seeing, this is shape of a rectangular box. We call it, this is the symbol of resistance. I think you know that. So resistance can be the symbol of resistance can also be in form of this. So this also stands for resistance. Please take note. A resistance in the diagram of a resistance can be a rectangular box like this, in case of like this one or this one. So we also have another one if it is being crossed like this. If it is being crossed like so, this is telling us that this resistance now is a variable one, unlike these two one. These two one now, this is what we call a standard resistor. Why this one? If it has a stroke like this, we call it a variable resistance. So take note of it. So as you have it now, that means that whenever we have an electrical cycle, we have the total EMF flow in that cycle. So which will be equivalent to the potential difference, because as you have the cell, it's going to, okay, you supply a cell to a cycle. How does it now work? So is it the more all the volts you supply that is needed for that cycle. So definitely we have that the EMF flow in a cycle equals to the potential difference when it is delivering current, then plus the lost voltage, and the potential difference when it is delivering current is denoted as IR from Ohm's law. I think you still recollect that as V equals to IR. Take note of that. This is your Ohm's law. So IR, why the lost volt now? The lost volt is equals to I, then small letter R. Definitely that we now have that V, which is the volts, equals to the potential difference when it is delivering current and plus the lost voltage. We have mean that if you try to factorize out current here, we have that current I equals to R plus big R plus small letter R. That means that our current, if you make the subject of the formula, we have V over R plus small letter R. So this formula stands for the formula for calculating the current flowing in an electric cycle. That means that when you have two more resistors, so this is the formula to calculate the current flow in that one. So we look into this example before we call it a day on today's online class as well. So example 1 now, we are given that two cells each of EMF 1.5. Let's say that we have cell A equals to 1.5 and we have cell B also equals to 1.5 volts. Now, so and internal resistance. So their internal resistance, as our earlier said, each cell will have its own internal resistance. So the internal resistance of this one is 2 ohms, and likewise this one is 2 ohms as well. So connected in parallel. That means that we have two cells A and B. Let's try to draw out the diagram for that. This is one, then this is another one. So this is 1.5, this is another 1.5. So this is, they are connected in parallel. Now, calculate the current flow when the current are connected to the 1 ohm resistor. So they now connect the external cycles to a resistance of 1 ohm. This is 1 ohm. This one is 1.5 and the internal resistance of it is 2 ohms. And this one is also 2 ohms. Now, so they said that we should calculate the current I that will flow into the circuit. Now, what to do is that since we have more than a single cell, you check out for the arrangement. Two cells, 1.1, 1.5. So definitely that since we have two cells now connected in parallel, that means that the total EMF for that one is 1.5, because I have earlier stated that when you have two cells connected in parallel, the summation of the EMF will be the EMF of one out of the entire cells. So that means that our total EMF equals to 1.5 volts. Are you following? Now, so likewise, we have internal resistance for this one, internal resistance for this one. So total internal resistance, since they are connected in parallel, I think you can still recollect the formula for internal resistance in parallel. It will be 1 over, since it is internal, it will be 1 over small letter r total equals to 1 over r1 plus 1 over r1, and which is 1 plus 1 over 2 plus 1 over 2. 1 over r total. That means that LCM here 2 into 1 plus 1 plus 1. That means that 1 over r total equals to 2 over 2. If you reciprocate it, that means r total equals to 2 over 2 as well. That means that total internal resistance equals to 1 ohm. Take note, why is the external resistance, capital letter R, equals to 1 ohms as well. So we now have to calculate the current flow in the cycle. That means that we use the formula that states that whenever we have more than resistance, in a circuit, that is that current, we have I, okay, we have V equals to R into bracket, anyway you know it, R plus small letter R. So making I the subject of the formula, we have that I equals to V over R plus R. And our V now, which is the EMF we are getting, which is the 1.5 volts, divided by big R 1 ohms plus small letter R 1 ohm. So that is a 1.5 over 2. That means that the current we are having here is a 0.75 units of current ampere. I think you are following. So we have many examples of cases now. What you should take note is that whenever you have more than two or more resistance, check for the connection. Is it parallel or is it in series? And you know the formula to find out that. And likewise, if you are having more than a single cell, you have a battery now. If it is in parallel, that means it will be the EMF of one out of the entire cell. And if it is in series, you sum up the total EMFs you are having together. I think you should take note of that as well. Then quickly, before we go to the electrical energy and then electrical power, so we have some formulas to define to state the electrical energy. We have electrical energy can be E equals to VIVT. We also have another one that I square RT, and we also have the third one, which is a V square R V square T over R. So all these formula now, they are using for calculating electrical energy. So it's based on questions you have been asked. If you are given current, potential difference and time, you make use of it. If it is current, resistance and time, you make use of it. And if it is voltage and resistance and time, you make use of it. And why electrical power? And you know that power equals to energy over time. So that means from this, if we divide this by T, we have electrical power can be IV, can also be from here, it can also be P equals to I square R, and P can also be V square over R. Any of these formula also stand for electrical power. And then the cost of running and appliances are so, which is being used extensively by the power holding company of Nigeria, is that we have the cost equals to the power, rate, and the time, everything divided by 1000. Because it is the power will be quantified in a kilowatt per hour. So this is the power, this is the rate, and then this is the time. So check for many of examples or workings on this relation. It is very, very essential. You first and foremost calculate your power, multiply by the rate, the time, and then divide the whole thing by 1000. So this is where we will be drawing the curtain of today's lecture. So when we continue, we start the normal time, my friend, which is a magnet. What do we mean by magnet, and what are the usefulness of a magnet? So you submit the assignment that will be given online as well, and make sure if you have any challenges, you can reach me on my phone number, which is the 080 60 73 6904. So I wish you well and you stay safe. Assalamu alaikum warahmatullahi wabarakatuh.